Hi students, this is Viswanath, Chemistry faculty for NEET and IIT exams. Now see the next topic, energies of orbitals. S, P, D, F, various types of orbitals are there. What are their energies? See here, the orbitals have the same energy are called degenerate orbitals. In S subshell, 1 orbital is present. In P subshell 3, D subshell 5, F subshell 7 orbitals are there. If any two orbitals have same energy, those are called degenerate orbitals. These type of orbitals we can find in p subshell. For example, 2p subshell, all the 3p orbitals have same energy. So these are called degenerate orbitals. That means 2px, 2py, 2pz are degenerate orbitals. In the same manner, 5d orbitals and 7f orbitals are also degenerate orbitals. Those are also having same energy. Next, in an atom, the most stable states or energy levels is called ground state, and higher energy states are called excited states. Okay, see the example. In hydrogen atom, 1s orbital is the most stable state. So 1s orbital is in ground state. An electron in the 2s, 2p or higher orbitals in a hydrogen atom is in excited state. So related to hydrogen atom, 1s orbital is the most stable one. So that orbital is present in ground state. Remaining orbitals 2s, 2p, 3s, 3p, 3d, all these orbitals having higher energy orbitals or higher energy. So these are present in excited state. Okay. Next, the energy of an electron in a multi-electron atom depends not only on its principal quantum number but also on its azimuthal quantum number. Multi-electron atom, that means more than one electrons are present, that is considered as multi-electron atom. So except hydrogen remaining, we can say multi-electron atom. In that, energy of the electron depends not only on principal quantum number, not only on main energy level, but also on azimuthal quantum number. Azimuthal quantum number represents subshell. So in case of multi-electron, energy of the electron depends on main energy level and also subshell. Okay. Say this, how these two influences the energy of the electron. That means for a given principal quantum number, S, P, D, F shells have different energies. So principal quantum number is the same. In the same shell, if we consider different subshells, they have different energies. What is the reason for this? The mutual repulsion among the electrons of various subshells in a multi-electron atoms. In a multi-electron atoms, electrons are present in different subshells. Among those electrons, repulsive forces are there. Those are responsible for different energies of different subshells. Okay. The stability of an electron in a multi-electron atom depends on the repulsive interaction of the electrons in the outer shell with the electrons in the inner shell. So if we take multi-electron atom, at the center nucleus is present. Last shell is called valency shell. It is also known as outer shell. Outer shell having electrons. Between nucleus and outer shell, inner shells also have electrons. Now inner shells having electrons, outer shell having electrons, all are same type of charged particles. So repulsive forces are developing between them. These repulsive interaction decides the stability of the multi-electron atom. Repulsive interaction is more, stability is less. Repulsive interaction is less, stability is more. Because of these electrons present in the inner shells, the outer shell electrons are shielded from the attraction of the nucleus. This is called shielding effect or screening effect. That means electrons present in the inner shells decreases the nucleus attraction on the outer shell electrons up to some extent and acts as a screen. So this is called screening effect or shielding effect. Say this, the shielding of the outer shell electrons from the nucleus by the inner shell electrons is called shielding effect. Okay, I hope you understood this one. Inner shell electrons act as a screen and decreases nucleus attraction on the outer shell electrons. This effect is called screening effect or shielding effect. The net positive charge experienced by the electron from the nucleus is known as effective nuclear charge. the net positive charge experienced by the outer electrons from the nucleus is known as effective nuclear charge. That means inner shell electrons decreases nucleus attraction on the outer shell electrons. In that condition, the resultant positive charge experienced by the outer electrons is called effective nuclear charge. This effective nuclear charge is less than actual nuclear charge. Suppose actual nuclear charge is 100%. 100% nuclear charge experienced by the outer electrons, but inner electrons decreases nucleus attraction on the outer electrons. Then in that 100% actual nuclear charge, only 80% is experienced by the outer electrons. That means 20% is decreased by inner shell electrons. This 80% nuclear charge experienced by the outer electrons is called effective nuclear charge. Okay. Next, despite the shielding of the outer electrons from the nucleus by the inner shell electrons, the attractive force experienced by the outer shell electrons increase with increase of nuclear charge. See this, outer shell electrons are shielded by inner shell electrons. Then also attractive force experienced by the outer shell electrons increase with increasing nuclear charge. Increasing nuclear charge means increase of atomic number. With increase of atomic number, nuclear charge increases, and at the same time, attraction of nucleus and outer shell electrons increases, though those electrons are shielded by inner shell electrons. So shielding, though they have shielding effect, then also with increase of atomic number, outer shell electrons experience more attractive forces. Okay. Next, for a given shell, that means principal quantum number, for a given principal quantum number, the effective nuclear charge experienced by the orbital decreases with increase of L value. L means azimuthal quantum number. For the same principal quantum number, if azimuthal quantum number value increases, then effective nuclear charge experienced by the orbital decreases. We have 4 types of orbitals, S, P, D, F. For these orbitals, L value is different. In case of S orbital, L value 0, P orbital 1, D 2, F L equal to 3 value. From S orbital to F orbital, L value increases. L value increases, then effective nuclear charge experienced by the orbital decreases. So S orbital will be more tightly bound to the nucleus because S orbital has more effective nuclear charge. That's why it is more tightly bound to the nucleus than P orbital, and P orbital in turn will be better tightly bound than the D orbital. So S orbital L value is less, so it is more closer to the nucleus. That means electrons present in this S orbital are more tightly bound to the nucleus than P orbital. P orbital is more tightly bound to the nucleus than D orbital. If we consider L value for these orbitals, L value increases, but closeness of this orbital decreases to the nucleus. Since the extent of shielding of the nucleus is different for different orbitals, it leads to the splitting of the energies of the orbitals within the same shell. See this, for the same principal quantum number, if we consider various orbitals, these orbitals shielding effect is different. S orbital is more closer to the nucleus means shielding effect is more than P orbital. P orbital has more shielding effect than D orbital. So extent of shielding effect for different orbitals is different. Because of this, those orbitals energies are also different within the same shell. Within the same principal quantum number, different orbitals have different energies because their shielding effect is different. That is, energy of the orbital depends upon the values of n and l. So energy of the orbital depends on two values. One is principal quantum number, another one is azimuthal quantum number. Now, how can we decide which orbital is higher in energy, which orbital has lower energy? For that, simple rule, n plus l rule. The lower the value of n plus l for an orbital, the lower is its energy. For a particular orbital, n plus l value, sum of principal quantum number and azimuthal quantum number is lower, then it has lower energy. If two orbitals have same value of n plus l, then the orbital with lower value of n will have lower energy. Two different orbitals have same n plus l value. In that case, which orbital has lower principal quantum number? It has lower energy. See the examples. 2s orbital. For this 2s orbital, n plus l value 2 plus 0 2. 3p orbital 3 plus 1 4. 2s has lower energy than 3p because 2s orbital n plus l value is lower than 3p, n plus l value of 3p orbital. Next, 3p orbital n plus l value 4. 4s orbital n plus l value 4. Different orbitals have same n plus l value. In that case, 3p orbital having lower n value. That's why its energy is lower. Okay. Next, in case of multi-electron atom, different subshells of a particular shell have different energies. Already we completed that point. In the same principal quantum number in multi-electron atom, if we consider different subshells, they have different energies. But in hydrogen atom, different subshells of a particular shell have same energy. But in case of hydrogen atom, 2s, 2p, 3s, 3p, 3d, these are higher energy states. In multi-electron atom, 2s energy is less, 2p energy is more. 3s energy is less, 3p energy is more. But in case of hydrogen atom, 2s, 2p, those are different subshells, but they have same energy. 3s, 3p, 3d, they have same energy. Because in this, no repulsive interactions between electrons, only single electron is present. That's why higher energy states, second level, second shell, third shell, having different shells, different subshells, those different subshells having same energy. Remember this point carefully. Next, the energies of the orbitals in the same subshell decreases with increase in the atomic number. Energies of the orbitals in the same subshell. In the same subshell, if we consider energies of the orbitals, their energy is decreases with increase of atomic number. Here atomic number means effective nuclear charge. See the example, the order of energies of 2s orbital. 2s orbital, if we consider different elements, hydrogen, lithium, sodium, potassium. In all these elements, 2s orbital, if we consider, from hydrogen to potassium, atomic number increases 1, 3, 11, 19. But their energies are decreased. Energy of 2s orbital of hydrogen greater than 2s orbital of lithium, greater than 2s orbital of sodium, greater than 2s orbital of potassium. So with increase of atomic number for the same subshell, the energy of the orbitals decreases. For this is the example. Remember carefully. Next, see the multiple choice questions. First one. The 2px, 2py, 2pz orbitals of an atom have identical shapes but differ in their orientation. Orientation means arrangement, direction. 2px orbital is present along x-axis, along y-axis, along z-axis. Their size is same, shape is same, spin may be same or different. But here orientation definitely different. Orientation means direction. In which direction those are arranged. Okay, we will meet in the next class.